Good evening, everybody, and welcome to Advanced Refrigeration Podcast. You're here with your host, Brett Wetzel, Kevin Compass, and we have a special guest. That's why we edit. A special guest, Ed Estberg. How are we doing tonight, Ed?
I'm doing fine, thank you.
So tonight, Ed is going to share with us. They have a rack out there that's a ammonia primary and CO2 secondary. So we're going to talk about the system for a little bit and maybe go through some of the piping. And I'll let you lead it away, Ed. I always ask all our guests how long you've been in the industry, what have you done in the past, and who you currently working for.
All right, I started as an apprentice mechanic in 1963 for Hussman Refrigeration in Northern California. Worked my way up to operations manager in charge of service and installation. And then in 1974, I started my own contracting business called Refrigeration Design. Ran that for 15 years, and that was purchased by Tyler Refrigeration after the partnership had some problems. And then in 1989, I went to work for Raley's, and I was responsible for all their engineering, construction, maintenance, everything to do with facilities until 2009 when I retired.
Mm-hmm.
And then about 7 years after I retired, they asked me to kind of help them through what California is putting the grocery industry through, going to natural refrigerants and kind of watch over their refrigeration engineering. And so that's what I've been doing as a consultant for the last 4 or 5 years.
So the company R&D that you started, was that strictly just, supermarkets and grocery store?
Yes, we specialized in light industrial, but mostly supermarkets and grocery. Yes.
Okay. Have you worked industrial refrigeration before? I mean, because I'm looking over at some of the prints, a lot of there's some subtle tones of industrial refrigeration.
I've been exposed to it. One of the first things that I had to do when I came to Raley's, we were building a new distribution center. It started in 1989, the year I joined.
Mm-hmm.
So I was responsible for overseeing that construction, the refrigeration portion of it.
Mm-hmm.
And it's got a large ammonia plant with about 18,000 pounds of liquid ammonia, liquid recirc. It's not low temp, just medium temp. So I had to learn a lot about industrial refrigeration right away when I went to work for Raley's. So I got involved in it that way.
Gotcha. So you were partnered up with Raley's for how long before you retired? Before you did the consulting?
20 years.
Oh wow!
So a long time. I've been in this business for 56, 57 years. So
that's amazing. Time. So looking over the thing, were you the one that helped engineer this? Were you consulting on this? I mean, how did this design come across?
Well, this was my idea to start with. Raley's has been looking for an all-natural solution for 2 or 3 years. And we've had a long history of working with direct drive compressors, mainly the 5H line Carlisle compressors.
Mm-hmm.
We have about 100 stores, no, maybe a little less, 95 stores with central systems in it.
Mm-hmm.
And these systems are kind of semi-industrial. They aren't really industrial, but they're open drive. They're a central system that runs everything in the store, from air conditioning to ice machines to ice cream to medium temp. And we've been very successful with this system for the last 30 years. We actually started with direct drives. Actually, when I was with Hussman built a product called the old TD system. I don't know if any of you are familiar with that, but it was, I would call it marginal at best, but it was an industrial type and direct drive system.
Yeah.
And it was way over engineered, had a lot of problems, hot gas defrost. They were air cooled for a while. They had oil equalizing problems. There was quite a few problems. Raley's had a bunch of them. And then we decided to fix those when I went there, and we did. And so one of the ideas about this ammonia over CO2 was that I wanted an all-natural system that was very much like the systems we already had installed. the service technicians didn't really need to learn a whole new trade to do this. So this system that I'm going to describe later on is really our two-stage direct drive system. And instead of the pipes going out to the evaporators, they go to two liquid feed systems, a low temp and a medium temp. And the compressors, I got Carlisle to build us an ammonia version of the 5-line. The motors are the same. The control panels are the same. The oil equalizing is the same. The condensing medium's the same. So there's a lot of things that are very similar to our standard store. And really the only difference is we put a liquid overfeed low temp and a liquid overfeed medium temp. Obviously we had to change the materials. Can't have any copper or brass in an ammonia plant. And that's basically the whole story. I mean, that's how we came about this system.
Okay. You want to start talking about the system? We went over the piping briefly the other day, and I was just amazed, because I was talking with Kevin before and about the system, and of how much energy you're basically saving. Not only do we have basically a 0 GWP, but on top of that, your compression ratio is absolutely nothing, because you're basically using compound compression in order to accommodate for the two different compression ratios, right?
Yes, the compression ratio on the high stage or the medium temp is pretty standard, but on the low stage, because we're discharging into the suction of the medium temp, its compression ratio is the same as the medium temp, maybe a little bit lower.
Mm-hmm.
So from an efficiency standpoint, it really is an efficient system. And then coupled with the fact that we have external motors and we don't have to run the waste motor heat through the compression cycle is a huge advantage, whether it be an ammonia over CO2 or a synthetic refrigerant. Just having external motors is about a 7% efficiency gain right off the top.
Well, that was one of the things that tripped me out, Kevin. When I was looking at the prints, I was looking to see how it was piped, and I was like, "Well, I don't see any liquid injection." And Ed stopped me. He's like, "Are they, refrigerant cooled compressors?" I'm like, "No." And then realizing I screwed up and was like, "Oh yeah, so it doesn't need it because you're not trying to cool down the windings, right?"
Yeah, and even if you did, even if you had it on a semi-hermetic, you probably wouldn't need intercooling because the compression ratio is so low, the discharge gas just isn't that hot. On the low stage, we're bringing back, because it's close coupled, maybe minus 10 degree gas,
Mm-hmm.
and it's leaving the compressor, at 70 or 80. So it's not, and then when you mix it immediately with a medium temp suction, it's just not enough to worry about. And that's true both on the ammonia and the synthetic systems. We don't use intercoolers at all.
You don't have any problem with oil overheating at all?
No, we don't have oil issues are just not a problem with these systems. The oil runs very cool. Now, I got to back up. On the ammonia side, it's a little bit more of a problem. We have to use water cooled heads
Mm-hmm.
on the high stage, not on the low, but on the high temp. We have water cooled heads because the discharge temperature get up to 250. It gets pretty hot.
All right, so you're compensating for that, feeding that hot gas into that stage by the head cooling, the water jackets in the heads, right?
Right, right.
Gotcha.
So, I mean, to describe the system without going over every pipe, it
Yeah.
basically is a two-stage system with a low temp and a medium temp. And we have liquid recirc CO2 tanks with thermal siphon cooling, one low temp and one medium temp. And then we circulate the liquid CO2 out to the fixtures. We use a 2-to-1 recirc rate, which means that for every 2 gallons of CO2 we pump out, 1 gallon comes back liquid and 1 gallon comes back vapor. So you get the phase change to keep your efficiency up. And that's really all there is to that system.
Now is that 2-to-1 supply and return? Is that standard on most systems that are designed this way?
I don't know the answer to that. Most of your industrial stuff is 3-to-1 or 4-to-1. Um, um, but in this system, it was designed 2-to-1 and seems to work fine. We have a couple other liquid recirc CO2 systems, and there are a lot of times when there's no liquid coming back at all. That we've been measuring the return suction line temperature, the return line temperatures on the overfeed racks, and sometimes they go to virtually no superheat, and so therefore you have no liquid coming back at all.
Okay.
And then we looked at some of the glass door cases. They only run maybe 2 or 3 minutes out of an hour.
Yeah.
The solenoid opens, you fill the coil with CO2, and it sits there and boils off for 20 or 30 minutes before it opens again.
Now, do you guys utilize floating head to even save a little bit more energy and floating suction on both your systems? I know you said that it's being controlled with CPC. I just didn't know if you guys were implementing anything extra to basically save a little bit more energy.
No, we do not use floating head pressure on the ammonia system. Um, but we do have a fairly sophisticated condensing system to trap as much of the waste heat as we possibly can for domestic hot water, space heating. And we also do a desuperheating loop where we, even in the summertime, we're taking that water we would normally use for space heating or domestic hot water and cool it with air to take load off of the open tower, so we're not using as much water. We're very conscious about wasting water in California. We're into what they call now a 1,200-year drought,
Oh, wow.
and water is a real concern for us. So we've gone to great lengths to um, reduce the water consumption. We developed a product called the DMCS, which is dual medium condensing,
Hmm.
and it's either air or water. And we've reduced our water consumption by 68% in wherever we've put it in the stores. So it's
Wow.
a substantial savings.
And you got it's an open loop system, I should say, and out in California, you guys do have a lot of calcium out in that water, yeah.
Yes, we do. That was a major concern of ours. With whether it be the ammonia over CO2 or a synthetic refrigerant system, are installing these DMCSs. And basically, for water treatment, we don't use chemicals. We use a Wave 2, which is an electronic unit, and then we use a LACO separator. And anytime the particles in the water grab some of the calcium carbonate and it gets above about 45 microns in size, then the separator separates it out. And once a day, we have a controller that opens a blowdown valve, and for about 15 seconds, we blow down the LACOS and blow all that crud out.
So I'm gonna actually show a picture of that. Currently, I have it pulled up. Um, I just want to you briefly explain, since we're talking about it already. Basically, the LACO system on what we see here and what we're doing.
Okay. What you have is two end centrifugal pumps. And in this case, they're 20 horsepower. And they pump, we're trying to get to around 400 gallons a minute. Goes through that wave electronic device and then into the LACOS. And it takes about a minimum of 4 and a maximum of 12 pounds of pressure drop across the LACOS to make it work properly.
Hmm.
And it's a centrifugal separator. The particles are separated out. The water goes out the top and then goes over to the condenser. If you want to slide down on that drawing,
Sure.
there you go. And goes through a strainer. And then you'll see two three-way valves there. And those are 4-inch valves, although recently we've gone to 6-inch because we couldn't get enough water flow through this 4-inch system. But those two valves are there that once a week we reverse the flow through the plate heat exchangers. When you read up on the maintenance for plate heat exchangers, if you have to run acid through them ever, they want you to run it through backwards, and they want you to run twice the GPM.
Mm-hmm.
Well, we can't run twice the GPM, but we can reverse the flow. So if we ever had to put acid in the system, we can just use these valves, put the acid in the tower, reverse the flow, run it for a day, drain and flush the tower, put the neutralizer in, and we're back in business. But we reverse them once a week just in case any particles get through the separator and get on the entering edge of a plate heat exchanger.
Mm-hmm.
I'm sure you've looked inside plate heat exchangers. The spacing between the plates is, less than 1/8 of an inch, so it's pretty tight. So any particles that might lodge in there, we blow out, blow back into the Lakos to be separated.
And that's what this motorized, it looks like a motorized ball valve here is at the bottom. That's basically your blowdown for that, correct?
The two of them in the middle, right next to the strainer, those are the reversing valves.
Yeah,
there
but
you go, up a little higher. Whoops.
Yep, these two right here.
Those two right there.
But over here by the Lakos, there's a motorized ball valve on the bottom of the Lakos, and that's for your blowdown to basically get any of the particles that drop out of that separator, correct?
That's correct. That's 1.25 inches. Yeah, just for the 15 seconds a day, we blow it down.
And I remember you telling me there was is the wave 2 is actually what's positively charging the particles inside the actual water that makes them stick together.
Yes, that's the easiest way to explain it. They take any dust particles or dirt particles that are in the water, and they charge them, and then the calcium carbonate is attracted to those particles. And as they circulate through, they pick up the calcium carbonate. And then normally, once they get to about 45 to 65 microns, they drop out in the tower. That's why when you use one of these electronic water treatment, the water's always clear, but the sump is always full of silt or dirt or calcium. Yeah. And in this case, before we allow it to settle into the tower, we separate it out with the Lakos, which is like 98% effective at 25 microns. So once these particles get up to 45 microns or so, before they can fall out into the tower, they're separated out in the Lakos.
Gotcha. So you're positive. So you're positively charging the particles, so they stick together, and that in turn makes the particles bigger because now they're collecting to each other, and then the Lakos basically catches all that debris and then gets blown out through the 1.25 inch line at the bottom, correct?
Well, that's not quite correct. They don't. The particles don't get together. The particles stay separated, but they attract the calcium carbonate out of the water. Okay. And it's settled, rather than settling on the pipe, it settles on this particle. And then when that particle gets enough calcium carbonate in it to be 45 to 65 microns, then it gets separated out by the Lakos.
Now, you also said at one point you guys do the blowdown the reverse flow every week.
Yes.
And how often is the Lakos then drained? Is that done when it backfeeds?
It never drains. All it does is blow down once a day at 9 o'clock in the morning. We open that motorized valve for about 15 seconds and blow whatever is trapped in there at that point. And in the wintertime, it's really kind of a waste because there's nothing in it.
Yeah.
Because we're not evaporating any water, and the water's not exposed to the air, so there's no particles in it. But in the spring and summer and the fall, some crud gets blown out of it.
How are you maintaining the 400 GPM? Is that done with circuit setters? Are you doing that with VFDs? I mean, how are you figuring out the GPM, or at least setting the GPM?
Well, we actually don't. We take whatever we can get. We size the pumps for 400, based on 90-foot head. And then based on the piping and the number of 90s that a contractor puts in or whatever, it's, it might be 400, it might be 380, it might be, 410. It doesn't really matter. It's way more than we need.
Gotcha. If you could briefly explain the air fluid cooler here, the Larkin, as well as the tower and how they work in conjunction with each other.
Okay, so the water comes through those three-way valves that we just talked about, goes through the condenser, comes out of the condenser, and goes into the air fluid cooler. So anytime that the ambient temperature is below 78 degrees, on this job, below 75 degrees, we turn the fans on the air fluid cooler, and we reject the heat from the water to the outside.
Okay.
Then the water goes up, and you'll see another three-way valve up on top of the tower. And when we're cooling with the air fluid cooler, we divert the water down into the sump rather than have it go over the media in the tower. And the reason for that is we found that even without the fans running the water over the media uses 50 gallons a day of water.
Oh wow. And it's probably putting debris on the filter, on the median anyway, right? Which you don't
Well,
want.
it's pretty clean, but
Okay.
we just don't want to waste that water.
Understood.
So then the water comes out of the sump and goes back into the pump. So when the ambient temperature gets above 78 or 75, we turn the fans off on the fluid cooler.
Okay.
And turn the fans on the open tower. And in Sacramento, or in Northern California, there's 8,760 hours in a year. About 75% of those hours are less than 78 degrees or 75 degrees.
Okay.
So it just kind of equates to the amount of water we're saving. The percentages are about the same because it doesn't evaporate any water when we're air cooled.
You know what? Let's start off the discharge line,
Okay.
I guess probably the medium temp, right? And then we can go to the low temp, which then we can feed back through the compressors.
Sure. The four compressors are tied in parallel, and the discharge line goes right from the compressors over to the condensers. Well, it goes to the heat reclaim heat exchanger first.
Right here.
And we're running a 2-inch water line on the other side of that plate heat exchanger. And we're trying to raise the water from about 80 degrees to 120, 130.
Okay.
There's about 75 GPM going in there. And depending on the load of the compressors and the load in the store, we get anywhere from 200,000 to 350,000 BTUs heat of rejection out of the heat reclaim plate heat exchanger.
Okay.
Then the vapor, we don't generally do any condensing in that heat reclaim heat exchanger. It's really a desuperheater.
Okay.
The gas comes out of there, it goes into a T and goes to two plate heat exchangers that are actually the condensers.
Condenser 1 and condenser 2. Yep.
Condenser 1, condenser 2.
Mm-hmm.
And they just run in parallel.
Mm-hmm.
The vapor, the warm vapor, is then condensed into a liquid, and it tees into a liquid line. There's a little tiny surge receiver there, goes through a dryer and goes over to the MT and LT liquid overfeeds.
Gotcha.
Now, one thing you're going to notice here, anybody who's looking at this or hearing this, who's familiar with ammonia will immediately say, "Where's your oil separator?" And there is no oil separator on this system. Historically, we have been very opposed to oil separators. In our opinion, they're a crutch for poor design. There's really no need for them. But in this system, if I do another one, and when we do another one, we will probably put an oil separator in, but it really doesn't need it. This plant's been running for 2 years, and it took us a little while to balance the oil out and getting it out of the evaporators. And it turned out it was really an easy process once we figured it out.
Mm-hmm.
On the medium temp, at night, we shut off one. There's 4 plate heat exchangers on the liquid overfeed rack. And we turn one off and let it sit for about 10 minutes. And then we open, there's a drain line right at the bottom of the evaporator, or the outlet of the expansion valve and the inlet of the plate heat exchanger.
Mm-hmm.
And whatever oil is in there always settles to the bottom in an ammonia plant.
Mm-hmm.
And we have a little ball valve, a little 3/8 ball valve. We open that ball valve, and then that oil at, let's just say 25 pounds pressure, is pushed into the oil reservoir that feeds the low stage compressors. And we'll go over that in a minute.
Okay.
So at night, every night, we shut one evaporator off, drain the oil out. Now, we measured the oil loss on this system, and it's about 8 ounces a day.
Mm-hmm.
Gets pumped out of the compressors into the evaporators. And so it's not very much oil when we open that little valve up. There's 4 heat exchangers, and the first 2 in line on the liquid line get all of the oil. The last 2 get very little. So we're talking about moving 3 or 4 ounces of oil out of the evaporators, the thermal siphon evaporators, or CO2 condensers, whatever you want to call them.
Yeah.
Back into the oil reservoir. And then we put our standard oil equalizing system. This is the same oil equalizing system we use on all our direct drive systems. And it's really quite simple. We pump oil from the low stage compressor's oil pump into a common line through a cap tube, and we pump then into the crankcase of the 4 medium temp compressors through another cap tube, which we've sized properly. We figured out how to size them. Mm-hmm. So there's no floats, there's no nothing on those. We're just always pumping oil from the low stage compressors to the medium temp compressors. And then on the medium temp compressors, they'll tend to overfill. So at a half a sight glass on the handhole cover, we drill a hole and put a valve. And then when the oil gets above a half a sight glass, it flows out of that valve through another cap tube and back into the oil reservoir. There you go, right up there. And then the oil reservoir is vented at a 10-pound check valve to the low temp section. So it's running about 2 or 3 pounds. You got 25 pounds on the crankcase of the medium temp. So the oil flows, if there's any oil at half a sight glass, it flows into the reservoir. If there's no oil in the medium temp, then you're just blowing a little vapor over into the low side. Doesn't hurt anything. And then when the low stage compressors run out of oil, get low on oil, they both have a float on them, and the float opens and we fill the crankcase of the low stage compressors. The oil is always moving in these systems from the low to the medium and back and forth. And it's very important with this type of compressor that you don't overfill a compressor. It's much more dangerous to overfill a compressor than to underfill, because you have an oil failure switch that'll shut it off when it gets low on oil. But you have no protection if you overfill and the crankshaft starts hitting the oil. Then you'll either scramble a compressor, break an oil screen, overheat the compressor. Lots of things happen when they get overfilled. So we developed this oil equalizing system 25 years ago and have used it ever since. On this job, we had to switch from copper cap tubes to quarter-inch stainless tubing.
Mm-hmm.
And fortunately, they make quarter-inch stainless tubing in any bore you want. You can get 25 thousandths or 55 thousandths. You just order the quarter-inch tubing with the right bore, and then you use compression fittings, and it works very well.
Gotcha. Now, there's two things I want to bring up. Most people might not know this, because most of our audience is commercial supermarket technicians. With liquid refrigerant and oil, usually liquid refrigerant will stay on the bottom, and oil will stay on the top, just like oil and water. With ammonia, it's different. The actual ammonia will sit on the top, and the oil will actually sit on the bottom. And is that the reason why you basically put the oil purge line on the bottom of the heat exchangers, Ed?
The oil in an ammonia system,
Mm-hmm.
when it's in liquid or any other state, will always be on the bottom.
Mm-hmm.
So when you run your liquid line, like over to our medium temp, the liquid is on the bottom of the liquid line, and it falls into the first liquid line going to the evaporator, and that particular evaporator will get most of the oil. When it
Okay.
goes through the expansion valve, the oil will be on the bottom. And so it tends to lay on the bottom, and the ammonia lays on top in the evaporator. And so when you open that valve, it'll just drain the oil out.
Gotcha. And you said it was hooked up. You said there was an additional line that was hooked up to the oil system somewhere. Is that correct?
Yes, yes, you're correct. The line, it doesn't show on this drawing, but the line coming from the evaporators, the oil drain line,
Mm-hmm.
ties into that line that is coming off the MT crankcases right at the reservoir.
Oh, okay.
So it just goes right into the reservoir.
Gotcha. So your expected pressures on this system as far as the oil. Now our suction is what, 2 or 3 pounds, right? For the ammonia side, correct? On
On
the
the
low temp.
low stage, correct.
Okay, so we're running 2 or 3 pounds there. We have that feeding into there, but this line right here is off of the actual oil pump. So be it's a Carlisle, you're going to have what, 25, 30 pounds heavier than what that suction is, correct?
No, the 5-line compressors run about 50 pounds of net oil pressure.
Okay, so we're talking like 52, 53 pounds, right?
Right, that pushes it over into the crankcase of the high stage, which are running about 23, 25 pounds.
Gotcha. Gotcha. And because this pressure right here is basically the same pressure, because it's at the same, it's basically using the same chamber. It's still the crankcase. And basically, because you're sucking off of the low temp, that's what's going to drive all this in through here, correct?
You lost me there. The
Okay.
oil from the low stage compressors leaves the compressor at about 52 or 3 pounds, let's say.
Okay.
And it goes into a line that's pressurized to 52 or 3 pounds through a cap tube.
Mm-hmm.
Then it goes, and the only reason the cap tube is on the low stage is to create an intermediate pressure so that if one compressor has a little bit higher oil pressure than the other,
Mm-hmm.
say one's at 52 pounds and one's at 50 pounds,
Mm-hmm.
then all your oil would come out of one machine, and we don't want that.
Okay.
So we put a cap tube in there so that there's an intermediate pressure, and both machines can pump into that line.
Gotcha.
Then the line goes over to the crankcase of the medium temp and goes through another cap tube, which actually creates the intermediate pressure,
Mm-hmm.
and then it flows into the 4 medium temp compressors. Whether they're running or not, even if it's sitting there off, oil is still flowing into it.
Oh, wow. Okay.
But then when it gets to half a sight glass in that medium temp compressor that's not running,
Mm-hmm.
it has to flow back to the reservoir.
So even if you have a little bit of oil coming back through your suction, You're not going to risk damaging it because it's going to be expelled through, through basically you're made an equalization line right here to make sure it doesn't overfill. Because has anyone that's ever worked on a Carlisle, they do not like oil being overfilled at all.
Right. As soon as it gets to half a sight glass, it starts pumping the oil out.
Since we're done with the oil system, I'd like you to explain this because unless anyone's ever worked on an older BJ's Wholesale Club on the East Coast or older industrial facilities, they've never seen head cooling kind of like this. I know
Okay, well, it's really a pretty simple uh, concept. This drawing shows water cooling on the load stage compressors,
Mhm.
and we did install it this way, but we found out that it created more problems than it helped. As a matter of fact, at one point we actually froze the water in one head and cracked the cover plate. Didn't hurt the compressor or the valve plate, but cracked the cover plate. So we've abandoned the need for water on the low stage compressors.
Okay.
So it's just on the 4 high stage compressors, and ammonia under when it's compressed gets very hot. The discharge temperature approaches 250 degrees, and it'll cook the oil and
Mhm.
it'll cook the compressors. So we're pumping from our condenser water. We're pumping about 10 GPM into each compressor, and Carlisle's recommendation is to run it through one head. If you look at their manual, you go through one head, you go to the next head, then you go to the next head on a 5H80. By the time the water gets to the 4th head, it's 50 degrees hotter than it is when it entered the first head.
Gotcha.
And we didn't like that idea at all. So we paralleled these. It's okay to go through 2 heads, but not 4. So the water comes in, and we tee it off. We go into one head, out of that head into the other, and then we do the same thing on the back heads, so that all the heads are really close in temperature.
Because then you're not basically have a nice, let's just say 75-degree head on that one, and then the other one adjacent all the way down. If you would have run in series, would have been 180 degrees or whatever. So you're getting
Yeah.
more constant head temperature across the board, which
Yes.
means your oil wear is going to be a lot more even, as well as probably bearing wear as well.
Yeah. Everything is better the more even you can keep the temperature.
All right. So what I see down here at CB, I don't know what CB is. Do you know what that is?
That's a balance valve.
Okay, so you actually have balance valves on here, because if anyone doesn't know, in industrial refrigeration, they either you can use glycol water, or sometimes they'll even use liquid coming from the thermal siphon off of the condenser
Right.
to basically chill the heads. Sometimes I've seen expansion valves also ran on this.
Right.
Um, there's a multitude of ways that you can do it, but this is the way that they decided to do it. So you actually have balancing valves on there.
Just
And
to
that's
make sure that we get the even flow across the heads. Yes.
and those are the ones that are basically getting you the 10 GPM that we were talking about before.
Yes.
So the temperature of the water coming in, typically averaging about what there, Ed?
It's condenser water at 78 degrees.
Okay. All right. And then so 78 degrees, um, both if I think when I was looking at the refrigeration schedule, basically the TD I think on these is about 10 degrees if I'm not mistaken. Is that right?
It's the system is designed on the condensing side for a 10-degree TD.
Mm-hmm.
But one of the things we learned, Rayleigh's has the ability to measure in real time our evaporator load
Mm-hmm.
and our EER on the mechanical system. And even though you fill out an RS sheet and you got 1.7 million BTUs heat load,
Okay.
that only occurs on a design degree day. And even that, it never, in our experience, you never get to that rated load.
Okay.
That's taken the case manufacturer's load and the walk-in box manufacturer's load, and you add them all and the air conditioning load. Well, none of these loads are all running at the same time. It never happens. Something's in defrost, something cycled. It's cooler outside than you planned, whatever.
Mm-hmm.
So you never have the full BTU load of the system.
Do you want to go through the air handlers, what you guys are actually accomplishing with this over here?
Okay, one of the other things we wanted to do with this is we wanted no synthetic refrigerants on the site. So
Okay.
all of our office air conditioning, our main cooling, our main store cooling, tech room cooling, meat prep room, all of those, we decided we wanted to do that without using any synthetic refrigerants.
Okay.
So we built little little chillers, a little board with a real small plate heat exchanger and a circulating pump. So each of the small loads has a board and a glycol loop in the air handler. And when you want cooling, you turn the pump on, little circulator pump, and you move maybe, on a meat prep, you maybe move 5 GPM. On an office air conditioner, you might move 2 or 3. On each stage of the main air conditioning, we move 10 GPM. And it just goes through the air handler, it goes through the plate heat exchanger. At the same time, you open a liquid solenoid on the plus 20 CO2,
Mm-hmm.
and you chill the glycol down to the way we sized it, about 33, 34 degrees. And so when you want cooling, you just turn the circulator on, open a liquid solenoid. That's
So
all that happens.
I'm not seeing it here. Is that not on this print where
It is
basically?
not on that print.
Oh, okay. So basically you're using the liquid medium temp liquid overfeed of the CO2 to basically chill down the heat exchangers, which chill down the glycol, which end up running to these same air handlers because basically you're doing heating and cooling. Is that correct?
Yes, but now there isn't a central glycol pump like is shown here.
Mm-hmm.
The at each air handler there is a little board about maybe 2 foot by 3 foot,
Mm-hmm.
and on it is mounted a little tiny plate heat exchanger, a circulator, and a liquid solenoid for the CO2 side. And you have a CO2 connection, and right at the air handler, when you want cooling, you turn the pump on, the fan runs all the time, and then
Okay.
you open the liquid solenoid and you achieve your cooling. What
Gotcha.
you're looking at here is the heating side, not the cooling side.
Okay. So I don't have that. I don't have that print available. Um, do they have something similar where basically like here I'm seeing looks like a bypass to basically bypass the supply if it doesn't need to call for heating, correct?
Yeah, this would be the 4 stages of heating, and you have a 3-way valve. Oh, excuse me, I take that back. This represents all of the different heating loads. There's only one stage of heating in the main air handler, and you
Okay.
have a 3-way valve. You're moving your desuperheater water all the time up through that air fluid cooler.
Hmm.
So when you want heat, all you do is operate a 3-way valve, and the hot water flows through the air handler. When you don't want heat, the hot water bypasses the air handler, and then the heat is rejected through the air fluid cooler. Summer and
Gotcha.
winter, doesn't matter.
Gotcha. So on this site, there's no synthetic refrigerants at all, no self-contains, no nothing. It's straight ammonia CO2, correct?
Unfortunately, I missed something I didn't know about. The owner of the building put an air conditioner in the elevator shaft. This has a 2-story mezzanine,
Oh, okay.
and the air conditioner in the elevator shaft is synthetic refrigerant.
And unfortunately, the other thing, if on the low temp CO2 liquid and the medium temp, basically this is going to look almost like a Walmart setup where you have that big green tank, which is considered the thermal siphon. You'll have the heat exchangers on the top. How many heat exchangers are there per thermal siphon there, Ed?
Well, no, wait a minute. The tank is not called a thermal siphon. That is just a tank.
Okay.
And above it are mounted, on the medium temp, there are 4 plate heat exchangers, and they are the CO2 condensers or thermal siphon condensers.
Mm-hmm.
So the liquid comes back into the tank, and the plate heat exchangers are colder than the tank, obviously,
Mm-hmm.
and therefore the vapor goes up the pipe, condenses on the plates, and drops back down into the tank. And that's a real inefficiency on this system, and we would not build another one like that. Hill has been a big proponent of thermal siphon CO2 cooling. These two happen to be built by Zero Zone, and they're a big proponent of it also. But it is extremely inefficient because you have to run those plate heat exchangers at least 10, in our case, 13 degrees colder than you want the liquid CO2 to be, to
What
make it condense on the plates.
what kind of superheat are you running on the ammonia side in order to achieve that 11 or 12 degree TD that you were talking about?
We only have about 5 or 6 degrees of superheat.
Oh wow.
It's really close. And it's close coupled to the compressors. So it's all in the machine room.
Yeah,
So that's a real trick, maintaining your superheat.
making sure you don't grenade that compressor with a whole bunch of liquid.
That's correct.
Okay. I mean, besides, so are you using, I'm assuming you're using some sort of electronic controller and electronic expansion valve on the CO2, or they,
Yes, I believe those are Danfoss MKVs. I think. I don't quote me on that. I don't know for sure. I can't
no,
remember.
that's fine. And just remember, guys, it has to be, it has to be non-brass, non-copper because we are dealing with ammonia here.
Yes.
So chances are, if I had to guess, I would say that those expansion valves might be, probably flanged in there, right? For serviceability.
No, they're welded.
Oh, they are.
We
Wow.
don't want any flanges. They're welded, but they do come apart.
Oh, so if the head goes bad, we can replace the head.
I don't know if you've ever seen I can't remember what they call them. It's got a solenoid, a shutoff valve, and an expansion valve all in one casting.
I know exactly what you're talking about.
And you can bolt them together any way you want, in any sequence you want. And they use the same welded body. It's really a very convenient device.
So what he's referring to, Sporlan makes something like that. Sometimes guys, you'll see like a pi valve, Sporlan EPR, and it's a one or two separate, or actually three separate functions, where one, you activate one solenoid, it activates maybe a medium temp EPR. You activate another solenoid and it operates a low temp EPR. And then if you operate both at the same time, I believe that's the way the function goes. Basically, it shuts the valve down. Hansen makes valves like this for industrial.
Right.
Danfoss makes valves like this. Basically, you can make that body do whatever you want based off of whatever head that you put on there. And I'll put a link in the podcast so you guys can check it out. It's actually pretty neat. So, like I said, you can make any one of these castings do up to almost, I think, 4 things. You guys went with Danfoss instead of using Hansen. Any reason why?
No, that was a choice of Zero Zone.
Oh, okay.
But we're happy with Danfoss. They work fine. We haven't had any issues with them.
And the system on the ammonia side holds approximately how much ammonia refrigerant?
There's 135 pounds of liquid ammonia,
Hmm.
3,000 pounds of CO2 in the medium temp, and about 1,000 pounds of CO2 in the low temp.
Wow. But you're also doing all your, the chillers and everything else, right? So
Yeah, it's everything in the store, all the mechanical equipment.
wow. And I see on the top of this receiver right here is if I had to guess, I would say that that's a high level indicator, like a physical.
It's a liquid probe,
Okay.
not high level, just a liquid probe.
Okay.
There's a funny story about that receiver. We put it in, and we had a real hard time getting the head pressure down to where we wanted it.
Hmm.
And it turns out we didn't vent that surge receiver. at the
Mm-hmm.
time.
Mm-hmm.
And the amount of heat in the machine room, we try and keep our machine rooms about 85 degrees. They're air conditioned, but
Mm-hmm.
we set it for 85 or 90 degrees. And it was above condensing. And the receiver with the stagnant liquid in it achieved the corresponding pressure, which forced our head pressure up. And so we had to properly vent that, and then we insulated it, and that solved our problem.
So let me just make sure I got this right. So, basically your receiver pressure would get too high. It probably almost even with your discharge, which then would just increase your discharge and become this would essentially become vapor locked. And so
No, no,
no?
what really happened is think about that vessel half full of liquid.
Mm-hmm.
And so you have a temperature pressure relationship, right?
Yes.
And if you don't vent it, then that receiver will warm up and you'll have at 85 or 90 degrees, you're going to have 165, 170 pounds of head pressure.
Okay.
And so it would back the liquid up into the condensers. And we couldn't get the head pressure down.
So you basically vented it to the inlet of your condensers, I'm assuming.
That's correct. We vented it to the inlet of the condenser, and then we insulated the receiver, and the problem went away.
Is there anything else you wanted to cover on this that's unique, like this air fluid cooler over here?
No, that's the de-superheater air fluid cooler, and that's where we take the heat out year round on the de-superheater circuit. Probably the one thing that some of these people might be interested in is the energy efficiency of this system, and it's not quite as good as our standard direct drive two-stage synthetic system.
Okay.
It's about 6 or 7% less efficient, and the reason for that is very simple. We have to run the compressors at 10 or 12 pounds or 10 or 12 degrees colder because of the inefficiency in the thermal siphon. So we're losing considerable energy there. And we're running a liquid pump on the liquid research system that we wouldn't normally run. So with that additional horsepower on the liquid research pump, and the fact we have to run at a much lower suction temperature, is what's causing the inefficiency.
But you're saving more money on other things. I mean, water treatment is extremely costly. It can it can cost a lot of money per year. And so because of the way you have the Lacos and everything else, I mean, you're basically saving that as well as the price of the chemical as well.
Yes, plus we use very little natural gas because we're able to heat the store and the domestic hot water without using any natural gas.
So
So
there's no
overall, utility-wise, this is a very efficient store. But just on electricity, it's not as good as it could be. And when we build another one, we will correct those problems. We
so
can't get away from the liquid pump problem, but we
Well,
can
the well,
certainly get down to, I'm going to guess 4 or 5 degree TD on the chiller, on the CO2 condensers.
so what about just going like straight transcritical? Wouldn't that be a more viable point at this point with how much CO2 you guys have on site? Seems like transcritical would be a bit more efficient, especially in like if you're running those ambient temps all year round.
Well, our experience, we don't have any experience with transcritical, but when we've talked to other people who have them and talked to them, talked about them, at least out here, the leak rate is about 100%. I mean, for some reason or another, something happens and they end up dumping their charge. So that's a concern. The other concern is all of the energy studies that have been done in our geographic area, where it gets to be 110, 115 pretty regularly. Now with a DMCS, we might do a lot better because we wouldn't have to go transcritical, maybe. But we're very concerned about the energy. And then we are very concerned about the high pressures. Our technicians working on pressures that, exceed 800 pounds. On this system, the highest pressure they see is about 450 on the medium temp liquid overfeed. And when you get up into the 9,000 pound pressure, we're very concerned about valve failures, ruptures, and maybe it's unfounded. I know there's 600 or 700 of these things installed in the United States, or maybe thousands by now. But Rayleigh's just hasn't gotten to the point where they're comfortable with it.
Yeah, a lot of the first systems that came out, transcritical, and Kevin, you can attest to this, that didn't have a lot of redundancy as far as if something happened to the one side of the CO2. So there, basically, if something happened, it's going to hit that relief pressure and blow. Is that correct, Kevin?
Yeah, that's a customer issue, 100%. Like that's the customer not wanting to pay for a backup generator or a backup system. Like we have original stores where they have that. We have no issues. Like it's that 100% redundant. Like that redundant system is 100%. Like they opted out of that. So like Hill, Phoenix, and like Zero Zone all push it. They're all trying to push it when they sell that, because I mean without it, if you lose power or if the rack goes down, yeah, you're going to vent the charge. But I mean, there is systems that are 90 bar systems. Like we have a Carnot system in Michigan that we do that it'll sit idle at 95 degrees and won't blow the charge.
Really?
How about 110?
Yep. It's all stainless. The whole thing is stainless.
Stainless.
Yep.
We've put auxiliary cooling units on on all our CO2 systems. Mm-hmm. We have a couple other ones too. Not ammonia, but other CO2 liquid research. And we have auxiliary condensing units hooked to our generators, which keep them cool during a power failure.
Yeah, I mean, without it, you're just wasting money. Yeah, I mean, without it, I mean, all you're doing is venting CO2 the entire time, especially with the 3,000 pound on charge and a medium temp. That's quite a hefty bill to vent out there. But so, I mean, yeah, a single unit, as an auxiliary is, I mean, you almost have to have it with something that big.
So we've looked at transcritical, and at this point, we felt this was a better option for us. Now, this is not going to work for every grocer in the country, but for us, because we already had the experience with the compressors and the oils and the controls, the only thing we had to learn was how to deal with the ammonia and the steel pipe and then the liquid overfeed. So
that was the question.
Easy transition for us.
That was the question I had, because like I know, a lot of places, they have the NIMBY approach where not in my backyard. I don't want any ammonia in my backyard. And like, there's stipulations where sometimes like ammonia plants can't be near school. What kind of, trials and tribulations did you guys have trying to figure out where this store was going to be? And like, what allowed this design to basically be in the area that it's actually in? Because you said this is in Northern Cali, correct?
Yes, it is, in the city of Sacramento.
Okay.
Interestingly enough, there was absolutely no issues.
Really?
I don't know if you guys have read the building code, but if you read the building code, there is no prohibition of using ammonia. You can't use it in a commercial building. You couldn't circulate it down to the cases. Mm-hmm. But if you have a properly vented machine room, and if you follow IIAR standards, there's no reason you can't use ammonia anywhere.
Okay.
The other concern that some AHJs worry about is the pressure relief if you have a high pressure release event. Mm-hmm. And so you have to do a plume study. We didn't have to on this one. But even if you did with 135 pounds total charge, the chance of us blowing 135 pounds all at one time is slim and none. But even if it did, and it vents out the roof, this machine room's up on the roof. Mm-hmm. By the time it dispersed down over the building and got down to the ground, you wouldn't be able to smell it. I mean, there's just not enough of it.
Yeah.
And remember, ammonia is not like propane or halocarb or synthetic refrigerants, it's lighter than air, except on a rainy or foggy day.
Mm-hmm.
So it vents and it goes up. It doesn't come down.
So you talked about having reliefs and stuff on the system, and it seems to me that it's, as far as controlling the head pressure, because you do have, basically the air fluid cooler and the BAC. I mean, you have a little bit of redundancy there that you can utilize. Yes.
Yes, but if we lost the circulating pumps, if we lost both pumps,
Mm-hmm.
we'd be down. Wouldn't matter how big we'd be in trouble.
Okay.
We have never lost any ammonia in this plant yet. We haven't had to ever put ammonia in it, but it's just, there's just not enough to create a danger in and around. This is right in a neighborhood with houses on two sides.
Oh, wow.
And it just wasn't. The interesting thing was, because of I was really concerned about the building department and the fire department.
Mm-hmm.
Before we started this project, I called them and sent them emails and said, look, we're going to put an ammonia plant in, and we want your input. We want to know how you feel about it. And so we sent them plans and we tried to communicate with them, and they said, we'll review your plans when you're done. We'll talk to you then. Don't bother us now. This went on for months, and then got time to issue the permit, and they had a whole bunch of comments about the electrical, about other things, the air conditioning, all kinds of stuff. There wasn't one comment about the ammonia or the CO2.
Oh, wow.
And so then I said, well, okay, we'll take out the permit, but now I'm worried about the field inspector. Once he really realizes that we got ammonia in this thing, what's going to happen? Not a comment, nothing.
Wow.
We went right through it, built it, and started it up, and nobody said boo.
Way.
Now, we did follow the code. If you read the code, the building codes defer to IIAR. I can't remember the chapter numbers, but we went through the IIAR chapters and made sure that we had an answer for everything that was in there.
So I'm looking at this. I mean, because I can't decipher, because I would need to really zoom in a little bit more, but I wanted to show like basically all the cases. Does all the medium temp also have doors on it? Is that what I'm looking here?
A lot of medium temp have doors, yes.
Okay, which makes it even more efficient.
That's just the electric defrost circuitry you're looking at there.
No, but the only thing I was saying that I noticed is that basically all the cases have doors on them.
Oh yeah, almost all the cases do. There's some open meat cases, one grab and go deli case, a big lineup, but all the beverage, dairy, deli, frozens, packaged produce, all have doors on them.
So did they give you numbers as far as the energy consumption, what it's costing them per month to actually run this thing?
Yes, I have that information, but we're not going to disclose it. I can tell you that it's really close to any of our other stores. From a corporate standpoint, they can't really see the difference. It's not a big deal.
No, that's what it might, because typical supermarket costs anywhere from like what, $35,000 to $60,000 in electricity per month to run.
That's a little high. Well, I don't know about where you come from. We're paying about on average 15 to 16 cents a kilowatt hour.
Okay.
And this store is not way out of the range of any of the other stores. And this is our largest store, and it's a flagship store.
Oh, wow.
So it's got a lot of equipment in it.
Yeah. So we have the compressors are 50 horsepower apiece, the 8 cylinders, and then the 15 horsepower, I believe, are
5H60s.
Yeah, okay.
They're nominal 60-ton machines, but because of the low compression ratio, you can drive them with a 15 horsepower motor.
Awesome. Kevin, did you have any more questions for Ed?
No, I mean, I'm still trying to kind of take it all in. I didn't get and look at the diagram. So, I mean, it seems pretty simple once you break it down. It's just, yeah, it's a two system. It's a giant 2-stage system with ammonia in it.
So
That's exactly right. Only it's not a giant. It's the same size compressors we put in all our stores.
Yeah. Except you're just using ammonia and it's in a small coupled space. I mean, it seems fairly simple. The oil system is kind of a little different than I'm used to seeing, but I mean that again, that's a custom off thing for you guys. So
and you said all the Rayleighs have that design of that oil system, correct?
Well, not all the Rayleighs, all the ones we've built.
Okay.
We've acquired quite a few chains, and so they have racks and they have all kinds of stuff in some of those. But when we build a store or do a major remodel, then this system, our direct drive system, goes in.
Now for Rayleighs, because they are dealing with ammonia, are they requiring their technicians to become RITA certified or Cairo?
Not at this point.
Okay.
This is the only ammonia one we have. Our distribution center techs are RITA certified.
Okay. Well, Ed, is there anything else you wanted to go over? Because I'm out of questions.
All right. Well, feel free to get in touch with me if you come up with some more when you edit this, and I'll be glad to share anything you want.
All right. Ed, I really appreciate your time. Thank you so much. And everybody have a good night.
All right. Thank you. Good night.